Hello and welcome to another one of D's ADD videos. Today we're going to be looking at the concept of resistivity and how it relates to resistance. Then after we establish that relationship, we're going to look at resistors themselves in series and in circuit, how to calculate equivalent resistances, and finally look at electromotive forces and the power that they generate and the power dissipated by resistors. Power in general. All right, so let's start with resistivity. Resistivity is basically a property unique to each metal that you can look up on a table or look up online nowadays, and it's going to be what dictates resistance that the electrons face when they're moving across the surface of a conductor. So mathematically speaking, when we're dealing with a symbol, you're going to look at this Greek letter rho. The SI unit is going to be the ohm meter. The formula is going to be the ratio of the electric field to the current density. If you remember, the current density is just the ratio of the current over the cross-sectional area that the current's going through. So basically, this will be related to conductivity in a reciprocal fashion. There is a reciprocal relationship between conductivity and resistivity. All right, and conductivity would be the ease with which the electrons go across the surface of the metal or conductor. Resistance and resistivity, the link is basically going to be dependent on more than just the value on the table. There are a few other factors that dictate the resistance. So what are some of the factors that affect the resistance? The type of the metal that is used definitely affects the resistance. We just discussed the resistivity being unique to each metal, and that will dictate the resistance that the electrons feel when they're moving on the surface of the conductor. Another important thing is the length of the wire and the diameter. Reason being is this is the relationship between, so the reason being is that this is the relationship between resistance and resistivity. Resistance equals the resistivity, again obtained from a table or internet or your instructor, times the length of the wire over the cross-sectional area that the current's traveling through. All right. One of the most important empirical relationships that you will see is Ohm's law. Typical conductors follow this relationship of voltage equals current times resistance. The SI unit is a volt, which is a joule per coulomb. If you remember, we encountered electric potential when we were doing potential energy per unit charge. Okay, so this is the same units. But this is a way to look at it in terms of current and resistance. Some elements or some materials will not behave in this typical linear relationship. If you have the current on the x-axis and the voltage on the y-axis, divide both sides by r, you get the slope of 1 over r for ohmic materials that behave this way. Okay, but semiconductors behave kind of like conductors and kind of like insulators, so they don't have this type of linear ascending relationship between current and voltage. So that's basically it, the concept of resistance and resistivity linked together. So make sure you start doing these problems and understanding the concept of resistance and resistivity, and check out the example videos as always. Practice, practice, practice. Thank you and have a nice day.